Hello friends, welcome back to the class of thermodynamics. In our previous session, if you will remember, we discussed about SFEE. What is SFEE? Steady flow energy equation. So we have already discussed in our previous session about SFEE, derivation of SFEE. Okay. Now in today's session, we will see the applications of SFEE. Means where this steady flow energy equation is used. Okay. And I already told you this is based on the first law of thermodynamics. So you can say this is the application of first law of thermodynamics. Now, application of first law applied to flow process. Why flow process? Because this is open system. We consider or we assume constant mass flow rate. Mass flow is there means it is open system. So it is flow process. Now, these are some examples of application of first law of thermodynamics to the flow process. Nozzle, diffuser, compressor, turbine, throttling device, boiler, evaporator, condenser and water pump. There are many more. I have given you some examples. There can be many examples. And most of these things are used in power plants. Most of these things are used in power plants. Okay. Some of these are power absorbing system, some of them are power producing system. Now what do you understand by power absorbing system and what do you understand by power producing system? And some are those are neither power absorbing nor power producing. So three categories are there like nozzle and diffuser. They don't consume power as well as don't produce power. Means so they belong to third category. Neither this nor that. Compressor. For operating compressor you need power. So it absorbs power. Means it consumes the power. Turbine. Turbine is used in power plant to produce the work. Turbine is used to produce the work. Throttling device. Throttling device is generally used to maintain the something. Like it is used in refrigerators. It is used in automobiles. Boiler. What is boiler? Everybody know. To heat or to generate the steam. Evaporator is also same thing. Condenser, it is used to cool something. Okay. Water pump is used to circulate the water or to take water from low height and throw it to higher elevation. So it also consumes the power or absorbs the power. Okay. So like this, there are some examples out of which some consume power or some produce power and some those who don't do anything. Now let us see one by one some of these. Now first nozzle diffuser. Okay, so this is the figure. Okay, here it is constant, it is pipeline in which this equipment is fixed. This converging from higher to lower cross section, from higher diameter to lower diameter. This is converging. This convergent shape is nothing but nozzle. Okay. Now this section from this middle portion to this higher diameter up to section 2. This is increasing diameter. And diameter is increasing, area is increasing, means cross section area is increasing. So this is diverging. So this is diffuser. Okay. Now this wiring like system, this is nothing but this is denoting insulation. So here we can see both things together. Nozzle as well as diffuser, both things are there. Just see it carefully and observe it, analyze it. So what did you observe? This decreasing cross section or decreasing diameter, this is nothing but nozzle. This increasing cross section, or you can say diverging, this is diffuser. So diverging means diffuser. Now I told you about mass balance and energy balance. Mass balance is also known as continuity equation. In our previous session of study for energy equation, I told you about this thing. Now, what will happen? Area into velocity. Product of area and velocity is constant. So, if area is decreasing, velocity will increasing. If area is decreasing, velocity will increase. This is the case of nozzle. Second case, when area is increasing, velocity will decrease because the product of area and velocity is constant. So this is the case of diffuser. And mass flow rate is constant. We already assume mass flow rate is constant. Means mass flow rate at the entrance is equals to mass flow rate at the exit. So this portion is nozzle, this portion is representing diffuser. Now here this wiring system I told you, this is insulation, means heat transfer is 0 and there is no shaft, nothing. And I told you nozzle and diffuser are neither absorbing system, energy absorbing system or power absorbing nor power producing, means work transfer is also 0, heat transfer and work transfer are 0. Keep this thing in steady for energy equation. So you are left with h1 plus c1 square by 2 equals to h2 plus c2 square by 2. Now someone can say, sir, what about potential energy? Yesterday I told you q plus h1 plus c1 square by 2 plus gz1. This is equals to w by m plus h2 plus c2 square by 2 plus gz2. Okay, insulation is there, so q is 0. There is no work transfer, so work is 0. But what about potential energy? So for potential energy, we will see how the terms are neglected. Suppose this horizontal line is our reference line, datum line, and this middle portion. If I will draw a line from here to this middle portion, okay. Now this is inlet, so from this datum to this height is nothing but z1. Similarly, here also is nothing but z2. Now what you can observe from here, z1 is equals to z2. So z1 and z2 will cancel out each other. So you are left with this formula only. So this is the formula of a steady flow energy equation per unit mass. Per unit mass. Why per unit mass? See here it is small, means specific. I told you specific quantity you represent by small letter. And what do you understand by specific quantity? Any property per unit mass. Per unit mass. So this is also per unit mass. Unit will be joule per kg, right, or kilojoule, depending on the unit or problem. So now this you can use in the case of nozzle as well as diffuser. You will, if you will solve the numericals, you will find how this can be used in the case of nozzle and in the case of diffuser. So I hope this thing is clear. This is the first application we have seen, or you can say we have taken with two examples. One is example is nozzle, another example is diffuser. Now next, compressor. This is the compressor. This compressor is attached to the electric motor. I told you compressor consumes the work. So when you switch on the electric motor, this compressor will start, means some work is done on the compressor. If you go for filling air in the tire of your automobile, your scooty, bikes, cars, you go to fill the air. What you observe there? There is one instrument. They switch on it, it will start and they will fill the air. That is nothing but air compressor. That is example of air compressor. Same thing is here. From one side air is going inside, means air inlet. From other side it is air outlet. Okay. Now this is the steady flow energy equation. Now in this case also this is insulated. Okay. And what about velocity? This is neither nozzle nor diffuser. So here we assume that change in velocity is very less, comparatively very less. Relative change in velocity is very less. So you can neglect this. But if in question velocity is given or any data is given to calculate the velocity, at that time you are not supposed to neglect anything. In question, heat transfer can also be given. So at that time, you should not neglect the heat transfer. Okay? If nothing is given for simplifying, in that case, you can take these other things 0. Otherwise, you can't consider it. Similarly, this Z1 and Z2. If it is given constant, nothing data is given in question or numerical, then you can neglect it. And if some height is given, okay, or difference in height is given, you can't neglect it. So main work, I told you, compressor is consuming work. So there will be some work. How much it will be? Here it is not plus, this is this side. This is by printing mistake. Here it is H2 plus W by M equals to H2. H1. In place of H1 there is H2. In place of H2 it is H1. This is printing mistake. Now someone can say, sir, why, if it is printing mistake, sir, then why like this? So you can take in another word, because I said it is consuming work, system is consuming work, means it should come negative, it should come negative. So this is represented in the form of negative. Why? How? Let me tell you. See, first consider this. Now Z1, Z2 is not given, so neglect this thing. You can neglect velocity as well. It is, we consider adiabatic insulated, neglect this. Okay, now you are left with H1, W by M and H2. Now sir, why you have written H1 plus Wm? It should be H1 minus. It will not be minus. Why? I told you compressor is consuming work, so it will be minus W. With sign, if you will put, it will be minus W. Here it is minus. Take it on the left side. It will be H1 plus. Okay. So this is the reason why it is written H1 plus, because it is consuming work, so it is minus. Here if it is minus, bring it this side, it will be plus. So you will get this formula. Okay, there should not be any confusion. Now next, throttling device. Throttling device is the thing which don't do any work. It is insulated, height is same, everything is same. Its work is only, or you can say throttling device process is constant enthalpy process. Whenever throttling device will come, you only consider constant enthalpy, means H1 equals to H2. This is a simple concept. If it is written throttling device or throttling process, just write H1 equals to H2. That's all. Next, boiler or evaporator. Now, this is the example boiler or evaporator. Design is changed. Okay, this you can use in power plant. This here example is given refrigerator. Inside refrigerator there is evaporator, evaporating is space. Now what is here? It is used to boil. Boil means there is heat transfer. Now here there is heat transfer, but there is no work. There is no work, there is only heat transfer. Okay, and how much it will be when you will solve, see, this equation. Q1 is with H1. Okay, so if you will neglect other things, you are left with Q by M plus H1 equals to H2. So Q will be, take this side, it will be H2 minus H1, and this M will also come here. So Q will be equals to M into H2 minus H1. Here W is equals to this much, there it will be Q equals to this much. Okay, see, Q equals to H2 minus H1. Okay, because there is no work in case of boiler and evaporator, so work will 0. Now it depends on the Z, means potential energy, and velocity. These things are nothing, no related to velocity. But there can be potential head, potential energy depending on the height of inlet and outlet. Okay, so these are some examples and these are the final output. So you have to note down all these things. These are important conclusions, can say, or examples or applications which you can see in your day-to-day life, daily life. Now condenser used to condense. In refrigerator you can see condenser is there. So what is the purpose of condenser? To cool. Boiler was used to heat, it is used to cool. In boiler, Q was H2 minus H1. See, Q is equal to H2 minus H1. So in condenser it will be opposite. It will be opposite, H1 minus H2. If you remember one thing, the another thing will be just opposite of it. That's it. Now turbine, opposite of compressor, turbine. So this is the complete formula. In place of enthalpy, we have written U plus PV. You can write enthalpy, you can write U plus PV. Whatever data is given in the numerical, based on that you can write either U plus PV or H. Now in turbine there is no heat transfer but there is work. So there will be work. There is no velocity. Okay. But what about Z? It is given Z2 is 0 but Z1 is having some value. Okay. So U is 0, delta U is 0, Z2 is given 0 and there is no change in velocity very much. So you can consider both velocity as same. So it will cancel out. So finally you will get this thing. P1V plus Z1G plus C1 square by 2 equals to P2V. Why not Z2? Because Z2 is given 0 plus C2 square by 2 plus W. If it is no data is given related to pressure, then you can neglect this term also. Okay. So depending on numerical, the things will become 0. You should remember this expression. Okay. Now from question to question, the different variables will become 0 or you can neglect it. Next, pump. This is the pump. What is the pump? It consumes the power and it throws liquid from one height to another height. You can see here. This is Z1 and from here Z2. It is taking water from this side and throwing it this side. So this is the formula and I told you because it is consuming work, so it is minus W. Okay. So this is the expression. I hope note down all these things. I hope these things are clear. Now we will see a numerical for sample. See, by looking it is looking very much big problem. But when you identify the things, it is very easy. Now what is written? A steam supply two streams which mix before entering the engine. One stream is supplied at the rate of this much with an enthalpy of this much and velocity of this much. So there is an engine, steam is supplied and there are two streams which are mixing. One stream data is given, its flow rate is given, enthalpy and velocity is given. For other stream, flow rate is given, enthalpy is given, and velocity is given. Okay. Now at the exit, the fluid leaves as two streams. In at the inlet there was two streams. At the exit also is showing something. Now data given is at the exit from engine the fluid leaves as two streams. One of water, one is of water at a rate of this much with the enthalpy this much, and other with velocity at exit is negligible. Velocity at exit is negligible given, and the engine develops means produces power. Must work is plus 25, and heat transfer is neglected. So you have to neglect the Q. You have to find enthalpy of second exit stream. Okay. Now come to expression. Given dq by t equals to 0, why? Neglect the heat transfer. Now do mass balance. Two streams are going in, two streams are coming out. So mass balance you have to do. Okay. So mass balance will be this W is nothing but small w. Mass flow rate. If you remember, I told you mass flow rate is either represented by small w or m dot. So this is small w. This is not work. This is mass flow rate. So W11 plus W12 plus 2 W21 plus W22. 1 represents for inlet, 2 represents for outlet, and this back 1 and 2 is for stream. So these data values are given to you. Now note, write down. You will get flow rate of second stream at the exit. This is coming this much. Now you are given enthalpy and velocity. So neglect other things. So mass flow rate into enthalpy plus V square by 2000. Now how this thing has came? Good question. I told you formula. What was the formula? H plus C square. C, or you can take velocity V by 2. Okay. Now why here 2000? And one more important. What is it? It is enthalpy is written in kilojoule per kg. So multiply with kg outside. This is kg per second. Multiply this thing, you will get kilojoule per second. Kilojoule per second. Yes. Okay. Kilojoule per second. Now for this side, why V square by 2000? Why 1000? Because here unit is kilojoule, 1000 times. Okay. So to make velocity component also 1000 kilo divided by 1000. See, enthalpy was in kilojoule. Already 1000 is there. But with velocity there is nothing related to kilo. So to compensate or to make velocity also 1000, divide this by 1000. So you will get this also kilojoule per second. This you are getting kilojoule per second. To make this also you have to multiply divide by 1000 to make it kilojoule per second. This is for first stream at the inlet. Similarly for second stream, then for heat transfer. Although this heat transfer is 0, here you can see, but we are writing the expression. Now coming to outlet side. What about outlet side? Here given fluid velocity at the exit is negligible. So velocity is already neglected. So you are left with only enthalpy. Okay? Plus dW by dt. Understand? Now put the values. W11 is given. H11 is how much? 2952. V11 how much? 20 meter per second. Okay. Similarly, W12 is given. H12 is given how much? 2569, and velocity 120. Put the values dq by t. I already told you it is 0. Why? Because In question somewhere it is given that heat transfer is negligible. So now coming to outlet W21, how much is given? How much it is given? This much. Okay. Now H21. H21 is given 420. W22. What about W22? You have calculated this W22 this much. Next H22. Any idea about H22? No. You have to find. You have to find this thing only H22. Now work, it is given power. How much? 25 kilowatt. Kilowatt means what is equals to this unit of power. Power is nothing but work per unit time. Work per unit time. Unit of work is joule. Per unit time. Time is second. Joule per second is watt. So it is given in watt. Given in watt. That's why everything we have converted into per second. You multiply with this. This is nothing but kg per second. That's why we have multiplied this thing with this. Okay. So depending on the given data, you have to see that unit of all the things should be equal. Then only you can equate this thing. You can get this equation. What happens in hurry? Okay, while solving the numerical, people used to forget this. You have to see the unit carefully. You have to match each and everything. If this is given in kilowatt or watt, kilowatt, so everything should come in kilowatt. So you have to take care of this thing. If it is given in kilojoule, then everything should be in kilojoule. If it is in kilojoule per kg, everything should be in kilojoule per kg. So you have to write the expression carefully. Now, after putting all the things, you will get finally H22, which is desired quantity which you need to calculate. Very simple problem. First, you were not knowing the exit mass flow rate, but you need this thing. So you have done mass balance. You have calculated this exit mass flow rate of second string. Then you have written this expression. Here it is given unit of watt work done power is kilowatt. So you have to get everything in kilowatt. How you can get this H11 is given in kilojoule per kg, but you want in place of kilojoule per kg you want in watt. How you will get? See, this unit is kilojoule per kg. Okay. Now if I will multiply with this mass flow rate, means multiply with kg per second. What will happen? This kg will cancel out. We are remained with kilojoule per second, and kilojoule per second is nothing but kilowatt. So like this you have to think and you have to write the expression. Otherwise, your whole work, your hard work will be of no use. Okay, so if the things carefully, write the things carefully, observe the things carefully, and put the things, you will get the output. Output was enthalpy of second exit string. You got it. I hope it is clear to everyone. That's all for today's session. Okay, thank you.